Hello everyone and welcome to the video lesson of physics. This is the second part of the topic scalars and vectors. And in this the second part, I'm going to show you how to add vector quantities or how to add vectors if they are parallel to each other or perpendicular to each other. So according to the new syllabus for O-level physics, these are the only two cases for which you need to learn to add vectors. The first case when the vectors are parallel to each other, moving in a straight line with respect to each other, that is kind of an easy one. So you don't need to draw like all sorts of diagrams to demonstrate the vector addition if they are parallel to each other. So whenever we add some vectors and then we get the answer, that is called the resultant vector. For example, if I have a box and a force of 5 Newton is being applied to the right side on the box, and there's another force of 5 Newton on the right side to the box. Now if I'm to apply a single force that would be having the same effect as these two forces combined, then that force would be called resultant force. So that would be a single force, but the effect of that force would be equal to combined effect of these two forces. So the question can be like this: here is a vector 5 newtons. Let's say the vector is a force. So the question might be like this: here is a vector 5 newton, and there's another vector 10 newton. Let's say in the same direction, and they would ask you to find resultant vector. So when you hear the word resultant vector, it means you need to add the vectors. So let us start with these cases in which the vectors are parallel to each other. And then we have the next case when the vectors are perpendicular to each other. So here we have the first one. We have a vector 5. So we don't know what quantity this one is. It might be force, it might be acceleration, it might be displacement, or it might be velocity. It can be any vector, but we have a vector 5 towards the right side, and we have to add it with another vector that is also having a magnitude 5 in the same direction. Whenever the vectors are added that are in the same direction, the resultant magnitude is added. For example, this one was 5 and this one was 5. You simply add these two because they're in the same direction. And that makes sense because let's say once again there's a box and there's a force of 5 Newton. Let's just call that the vector is a force. So there was a force of 5 newtons towards the right. There's another force of 5 Newton towards the right. And that implies that if you want to find the combined effect of these two forces, the overall force would be 10 Newton. So in this case, the answer would be 10. Since we don't know what quantity it is, and if they have, like in this case, we have specified here that these are the force vectors, so you can assume that the total answer 10, it is in newtons. And then you need to draw or represent the vector as well, and we draw it in such a way that the length of the vector, new vector, is double than the length of each one of these. So basically we have added their lengths as well. So the length of the line is the length of the final line, or the resultant vector, equals to the length of this one plus the length of this one. And that is our final vector. It is in the same direction towards right, but its magnitude is 10. We simply added these two. And you see, if you draw it like this, 10, You have written that the magnitude is 10, but once you're drawing it, you draw it like this. That one represents that the magnitude appears to be same as of 5 Newton. And we studied in the previous part that the length of the line represents magnitude of the vector. Magnitude once again means the numeric value, the number that is written with the vector quantity. For example, if there's a force, once again, force is an easier example, so we like to break it down in terms of force. So let's say there's a force of 100 Newton towards right or towards east. Then this thing is the direction, this thing is the unit, and this 100 is the numeric value called magnitude. So magnitude is always represented with unit. Otherwise, we're not able to understand like what do we actually mean by that magnitude. Because even if we are talking about force, it might be kilonewton as well. It might be meganewton as well. So unit should always be there, and basically a combination of a number and the unit is collectively called magnitude. Moving on to the next part, the second example, we have a vector 5 Newton towards the right side, and there's another vector negative 5 newtons towards the left side. And since it was minus 5, this one was minus 5, and that's why the direction of the arrow is opposite to the direction of this one. So the negative sign with a vector represents direction. It has nothing to do with the magnitude. I mean, magnitude wise, 5 Newton and minus 5 Newton, they are just the same. So a force of 5 Newton and minus 5 Newton, the impact of these two forces would be same. So don't think of it in terms of mathematics that minus 5 lies on the left side of the number line. So the difference between minus 5 and 5 is 10 units. So minus 5 would be 10 units smaller than 5. No, it's not. The negative sign represents nothing but direction only. So just ignore the negative sign because it is just representing direction, and we know, and they have drawn as well, that this vector is backward. Since 5 Newton was forward, so minus 5 would be backward. Now if we add these two vectors, 5 Newton plus the other one is minus 5 Newton, the final answer would be 0. So the resultant force is 0. There's no force, there's no resultant force acting on the object. Because the forces were equal and opposite, they cancel out each other. Then we have the third part, the third case. We have a vector of 5 Newton and we are adding a vector of 10 Newton, a force of 10 Newton and a force of 5 Newton. And you notice one thing, that the length of this line, let's say if this one is representing 3 centimeter, then this one is double the length of the previous one. So this one would be approximately 6 centimeters. Ideally, it should be 6 centimeters. It should be double the length of the previous one. Because once again, length represents the magnitude of the vector. So if we add these two, since they are in the same direction, we simply add these two, and when we are drawing it, more importantly, whenever you deal with the vectors, draw the diagrams with the help of a ruler. All right, freehand drawings, they are not acceptable, and you would be just losing your marks for no reason. And then the length of this one of 15 newtons should be equal to the length of this one plus the length of this one. So if this one was, let's say, 3 centimeters and this one was should be of 6 centimeters. Then for 15 newtons, it should be 3 plus 6, it should be like 9 centimeters in length. All right, so these measurements I'm just referring here for an example. It might be a little bit different once you do it on the sheet of paper. So going to raise it off from here. So the final answer is 15, and once again, if the vector is a force, it would be 15 newton in the same direction, which is towards the right side or towards east. Then we have the next one. We have to add 5, and if it is a force, like we said, we are dealing with the forces, so we have to add 5 newtons with negative 10 newtons. Now if we compare these two, negative 10 newtons has more magnitude than 5 newton. Basically, the magnitude of minus 10 newtons is double the magnitude of 5 newton. Like I said, the negative sign just represents direction. So just you ignore the negative sign. It was just there for the direction. Now in terms of the number, numeric value, this force is twice the size of this one. Now when you have to add them, you simply add it arithmetically. 5 plus minus 10, then the answer would be negative 5. So means we'll be having a force of negative 5. Negative 5 simply means the force in the opposite direction to 5. So we'll draw a vector which has the same length as of this one, because this one represents 5 newtons. So it's the same length as of that one, and towards the left, and it would be 5. If you want to write Newton here, you can. Like I said, we are representing forces here. Now the thing is, the other way, the easier way of sorting out the direction is the resultant force would be in the direction of the larger force. Or if it's not force, if some other vector, displacement, acceleration, or anything, then the resultant vector would be in the direction of the bigger vector. And when I say the word bigger vector, you have to ignore the negative sign. All right, don't just compare that 5 is bigger than minus 10. Mathematically, 5 is bigger than minus 10. So the final vector, the resultant vector, should be towards the right side since 5 is greater than minus 10. No, it's not. Here, the negative sign is not basically representing a number. Negative sign is something else. It is just telling you the direction. And the actual value of the force is 10 Newton. So you move towards the right side, sorry, towards the left side, and the final force in this case would be 5 newtons towards the left side. Then we have another example. We have a force upward, we have a vector upward that is 10 in magnitude, 10 Newton, let's say, and there is a force downward of negative 5 newtons. First of all, let us find the magnitude of the resultant force. So it would be 10 plus minus 5. All right, and mathematically we understand that this would be 5. And it doesn't really matter which one vector do you consider the first one. The answer would be same in any case. Let's say I consider this is the first one and this is the second one. So I'll be writing minus 5 added with plus 10. The answer would still be 5. So whatever vector you choose first, it does not affect the magnitude of the resultant vector or the direction of the resultant vector at all. Now we understand that the answer for the resultant vector would be 5, but then the question is in what direction? Since the bigger vector was 10 Newton and it was upward, so the direction of the final one would also be upward. It would be something like this. And you need to be very careful with the size. If the answer is 5, it should be corresponding to the length of this one. All right, it should be pretty much the same. Ideally it should be exactly the same, but at least it should be pretty much the same. There should not be a dramatic difference in their lengths. All right, so then we have the second case, if the vectors are not in the same direction and not even in the opposite direction. So they are not parallel to each other, they are not anti-parallel to each other. We cannot simply add them, we cannot simply subtract them, because if, like we studied many examples in the previous slide, if the vectors are in the same direction, we simply add them, and if the vectors are in the opposite direction, then we have to subtract them to find the resultant vector. But what if one of the vector is, let's say, towards the right side, and there is another vector that is, let's say, upward? Now you need to add these two. We cannot simply add them because they are not in the same direction, and we cannot subtract them because they are not in the opposite direction. So what do we do in that kind of situation? The answer is, there are two methods which you can apply to find the resultant vector. One is a general method that can be used to solve any kind of vector addition question, whether they are parallel, perpendicular, or at any angle. That method can be used to answer any kind of question. That is called scale diagram, and that is carried out by head to tail rule. The other method is by using a mathematical concept. We have a law that we call Pythagoras theorem. Yeah, I'm not really sure about the spelling, you can just check it out. So Pythagoras theorem is a law of mathematics uh, which applies to a right angle triangle. And according to this formula, if you have a right angle triangle, so let's say here we had a right angle triangle. This one angle is given as 90 degrees. So this one you can call base, this one would be your perpendicular, and this is the hypotenuse. The longer side is called hypotenuse, and the other two sides can be changed uh, or can be used interchangeably. What I'm trying to say is you can call this one base perpendicular and you can call this one base. It doesn't really make any difference. All right. So the theorem states that the hypotenuse squared equals to base squared plus perpendicular squared. So out of the three sides, if you're provided with any two, you can find the third one. So it's not only used to find hypotenuse, you can find base, you can find perpendicular, provided the other two sides are given. Sometimes the other two sides are given directly, sometimes you have to apply some properties indirectly, but uh, as the syllabus demands, the other two sides would be given directly. So we have an example. We have a vector of 8 Newton. There is a vector of 8 Newton. Let's say towards, according to the example, the vector 8 Newton is towards the right side. So that was 8 Newton. And there's another vector that is directed upward, and that is 6 Newton. So let me decrease the length of this one a little bit, because since this one is 6 Newton, so it should be, in principle, it should be less than that of 8 Newton in terms of length. So this one is representing 6 Newton. And these two are forces. All right, just Force is kind of a very good example to consider vectors, easy to understand. There are some other vector quantities as well, acceleration, velocity, but I don't like to use those ones for now because the students are generally not familiar with. Force is something that we study in our middle school science as well. So there's another vector 6 Newton that is upward. So we have to add these two. I can draw a plus sign, addition sign over here because we need to add the vector 6 Newton with a vector 8 Newton. Now the thing is the final answer cannot be 40 Newton. It would have been 40 Newton had the vectors been in the same direction, but they are not. The final answer cannot be 2 Newton because you cannot simply subtract these two. It would have been 2 newtons had the vectors been opposite in the opposite direction. So not in the same direction, not in the opposite direction. So what you have to do is you can form a right angle triangle using these two vectors. Now since this vector is towards the right side and this vector is upwards, we can form a right angle triangle with it. So all you have to do is um, pick up the second vector and place it at the end of the first one. I repeat, pick up the second vector and place it at the end of the first one. So how do you do that on paper? So you simply ignore the first one and you assume that you're holding the first vector and you place it right over here. All right, so simply you can draw a line that is parallel to this one or that is congruent to this one. Congruent means in the same direction and of the same size. All right, then the thing is any of these two vectors can be called first one and any of these two can be called the second one. So all you have to do is just place one of the vectors at the end of the first one. All right, so you can do it either way. You can place this one at the end of this one or you can pick up the second one, all right, 8 newtons, and you can place it at the end of the first one. So you don't right now you don't need to like learn these terms, but uh, this end of the vector is called tail. This one, the side with the arrow, where the arrow is pointing at the last part, that is called head. So basically we hold up the second vector or one of the vector and we place it at the head of the first one. So what I'm going to do is I'm going to hold this one and I'm going to place it over here. Once you're done with this step, and once you're doing on the sheet of paper, I mean it would be drawn there, it would still be showing over there and no need to worry about it. Just ignore this, assume that we have placed the first one or one of the vector at the end of the second one. And then in the next step what you have to do is you draw a line. You draw a line from the tail starting point towards the head or towards the ending point. And say that I started from this side and I was going over there upward. So the direction of arrow should be uh, top right corner. Now we do have a right angle triangle. Since this angle would be 90 degrees, 8 Newton was towards the right side, 6 Newton was towards 6 Newton was upwards. We do have a right angle triangle. According to or for that right angle triangle, this is your hypotenuse and this hypotenuse is representing the resultant vector. If somehow you're able to find the length of the side h, you'll be able to find, or you'll be able to answer for the magnitude of the resultant vector. So you can call this one base and this one perpendicular. Once again, perpendicular and base, they can be used interchangeably. So let us plug the values in the formula. So hypotenuse square, we write it as it is, equals base squared. So base was 8, we write square of 8, plus perpendicular was 6, we write square of 6. And then we sort it out, like 8 squared means 64 plus 36, that would be 100. But you were not supposed to find the value of h squared. You have to find the value of h only. So you take square root on both sides and the answer would be 10. And if these are forces, all of these are forces. So this answer for a plus b, or for the resultant vector, would be 10 Newton. And in terms of direction, you can say it's in the top right corner. And if you want to use a mapping system, you can say it would be northeast. All right, because for the map we follow a convention. All right, and the convention is, on your sheet of paper, the side pointing upward represents north, downward represents south, towards the right side represents east, and towards the left side represents south. So since your vector is somewhere in this direction, you can say it is directed northeast. And what is the value of that resultant vector? 10 newtons. Since the vector in this case is force, we have assumed it is force, so that's why I'm saying in newtons. So the value of the resultant vector is 10 and its direction is northeast. And you see, the answer for the resultant vector is not 14. You were not able to simply add them. It was not 2, because you were not able to simply subtract them. It is somewhere in the middle. It would be greater than 2 and it would be less than 14. All right, let's move on to the next thing. This is called the scale diagrams. Two or more vectors can be added by using the scale diagrams. No matter if the vectors are parallel to each other or perpendicular to each other or at any angle, you can simply add them by using this method that is called scale diagram. So you might have seen this thing, the concept of scale. We always see it everywhere, like in your history or geography books. You might have seen some certain maps or the uh, maps showing the topography of a place, or the world map itself, or the climate maps and stuff like that. So in those maps, the actual distance between 2 points, let's say between two cities, is compressed down to a certain scale. So let's say the actual distance between two cities is um, 300 kilometers, but on the map we don't show the distance to be 300 kilometers. If you measure on the map with the help of a ruler, that distance might be 6 centimeters, or the distance might be 10 centimeters, depending on the size of map. So the thing is, a certain kilometer are represented by a few centimeters to use or to construct a suitable scale so that your map would not be as big as the actual size or the actual distance between the two cities. Otherwise, it would make no sense. It would be like colossal. So that is called drawing a scale. And this is something that can have different variations. Two students are doing the same question, their scale might be different. What is the criteria? The only criteria for a scale is it should be a normal looking scale. It should not be too dramatic. When I say too dramatic, it means the scale should not be too small, too big. And the length of the lines that you're drawing on the paper should be normal. Not too large that it is sticking out of the sheet of paper, or not too small, kind of microscopic. Not literally microscopic, but just a metaphor. So let's see, how do we solve a question like this? So the question is, find the resultant vector r. You need to add the vectors and the angle of action. All right, the angle of action I'll explain later. What do we mean by angle here? Of two vectors, 30 meter east and 20 meters south. So the vector would be a displacement. We study in the next chapter in detail what do we mean by displacement. So one of the vector is, you can call d1, 30 meter, and that is directed towards east. The second vector is 20 meters, that is directed towards south. So if I can draw a map here like real quick, just to show the directions. So this one would be representing north, this one would be representing, sorry, south, this one is representing east, and this one is representing west. So we have one vector that is towards east in this direction, the other one is towards south. You cannot find the answer for the resultant vector by adding them, since they are not in the same direction. You cannot find the answer for the resultant vector by subtracting them, since they are not in the opposite direction. So what you have to do is, one way was, you can use the, once again you can make a right angle triangle using them, and you apply the Pythagoras theorem, and try to follow that method if they have not specified that you have to draw scale diagrams. So let us construct a suitable scale. So the first vector is 30 meters. If I don't make a scale, then I would have to draw a line that is 30 meters on the sheet of paper, and that is practically impossible. And for the other one, I need to draw a line that is 20 meters towards south. The length of the line should be 20 meters on the sheet of paper, practically impossible. So what if I say that while constructing the scale, or while constructing the map, 1 meters or 6 meters, whenever I get 6 meters, I'll be drawing a line of 1 centimeters. Every 6 meter of the actual value represents 1 centimeter of the value on the paper. So we have to draw two vectors. The first one was how much it was, 30 meters. So if 6 meters represents 1 centimeter, then 30 meter would be represented by 5 centimeters. All right, so because 6 5s are 30, so you have to multiply 1 by 5 as well, or you can cross multiply, simply cross multiply. And you would know that if 6 meters is representing 1 centimeter, then 30 meter would be representing 5 centimeters. And when I need to draw a line 20 meters, sorry, the other one is 20 meter. I thought it was just 18. For 20 meters, the scale would be in decimals. You can do in the decimals, but right now I'm not getting into that. I say this one, 5 meters represent 1 centimeter. So if 5 meters is representing 1 centimeters, then 30 meters would be represented by 6 centimeters. And then 20 meters would be represented by 4 centimeters. All right, if you don't know that, just once again I'm saying cross multiply, like 5, write 5 here, 1 here. Now you have to represent 30, so 30 would be corresponding to x. From there you cross multiply and you can find the value of x, so you can write 6 here. Sorry, the working was here. Yeah, so you can simply cross multiply to find the value that has to be represented in centimeters. So I'm going to raise these one off for now because I know 30 meters corresponds to 6 centimeters and 20 meters corresponds to 4 centimeters. I'm going to raise this one and I'll be writing it on the data itself. So for this one, 30 meters, I need a line 6 centimeters, and for 20 meters, I need a line 4 centimeters. And what is the scale? Well, the scale is this one. For every 5 meters, I'll be drawing a line 1 centimeters. That is my scale. You can give, matter of fact, you can give the heading as well. This is a scale. Now, let us draw a line that is representing 30 meters. So it should be of 6 centimeters on the sheet of paper, and that should be pointing towards east. So I may not be using the scale right now on the computer. Um, but I'll show you the method anyway. So let's say this line is representing 6 centimeters, and that has to be directed towards east. So I can draw an arrow like this. Arrow can be drawn anywhere on the line. All right, you can draw at the end, you can draw over here or anywhere. So this line now, which is only 6 centimeters, but uh, in real life it is representing 30 meters distance displacement towards east. Then we have another one that is 20 meters towards south, and we stated that 20 meters, according to our scale, 20 meters would be 4 centimeters only. So we'll be having 4 centimeters, a line that is 4 centimeters. And if you want to avoid an extra step, all you can do is draw the second line directly at the end of the first one. So the first vector ends over here. You can draw the second one right at the end of the first one. So yeah, so 4 centimeters, let's say this one would be, so the total was 6, so this one might be 4 centimeters. So yeah, pretty much this. I'm not using the ruler right now. Well, let's say this line is now 4 centimeters. On the sheet of paper, once you're drawing in the exam, it has to be exactly 4 centimeters. So we write 4 centimeters here. We draw the arrow. It has to be towards the south. Okay, the thing is, it has to be towards the south. So for the same length, let's put it downward because it has to be towards the south. On the sheet of paper, south is downwards. So we draw it like this. Then we draw the arrow as well. Arrow represents the direction. So 4 centimeters in length, which is in real, for the actual thing, it is representing 20 meters. Then the final step is draw a line from the starting point towards the end point, or from the tail towards the head of the second one. So I'm going to draw a line with this one. We stretch a line from the starting point and we join it at the ending point. And the direction would be away from the starting point and towards the end point. Away from the starting point and towards the end point. Now, the next thing. So this one line was 6 centimeters. This one line is 6 centimeters. And this one line is 4 centimeters. You have to find the magnitude of the resultant vector. So all you have to do is find the length of this line with the help of the ruler. Just place the ruler along this line and find the length of this line. Now this thing can also be done by using Pythagoras theorem. All right, once again, if you see this is the right angle triangle here, because the two vectors were perpendicular to each other, are perpendicular to each other, so this is a right angle triangle, and you can find the uh, this length, or you can find the value of hypotenuse using the Pythagoras theorem once again. But when we are doing with the scale drawings, when we are having the scale drawings, that it is better, it is preferred that you use the ruler to measure length of this line. But off camera, all right, when the camera is not around you, you can, I mean, you can sneakily measure length of this line using Pythagoras theorem, and no one should know that. So since I'm not having the scale, I'll just use the Pythagoras theorem to find the value of this green line, and I'll just assume and I'll just pretend that I've used the ruler. So 36 plus 16, and then I have to take square root of it, and that is 7.2. So yeah guys, I didn't use any Pythagoras theorem, I used the ruler, and the length was 7.2 centimeters. All right, now you can't tell that if I have used the ruler or I have used the Pythagoras theorem. Nobody knows. All right, so 7.2 centimeters is the length of this line. Now for the final step, this 7.2 centimeters represents how many meters of the real physical quantity. Since 6 centimeters was not 6 centimeters for the real quantity, 6 centimeters was representing 30 meters. 4 centimeters was representing 20 meters. So 7.2 centimeters represents how many meters? For this one, you go back to the scale and you understand this thing. Our scale was every 1 centimeters represents 5 meters. So 7.2 centimeters would be represented by x meters, or you can simply multiply, right? 1 centimeters represents 5, 2 centimeters would represent 2 times 5, 3 centimeter would represent 3 times 5, 7.2 centimeter would represent 7.2 times 5. Once again, if you're not good with it, you can use the cross multiplication method. So I hit it on the calculator. Just give me a moment. 7.2 times 5. It is 36. So what I get is 36 meters. That is the resultant, that is the magnitude of your resultant vector r. All right, this one you can represent by r because they stated over here the resultant vector, you can call it r. All right, then the next thing was to find the direction of or the angle theta of the resultant vector. Now at this stage, at your level, they ask you that you need to show the angle or you need to measure the angle with respect to uh, what direction? Let's say with respect to north, angle between north and resultant, or angle between east and resultant, or something like this. So the angle is normally mentioned in such a way that you will be provided with where do you need to start measuring the angle from. For instance, if you have to measure the angle between east, alright, and the resultant vector, then the required angle would be this one, and you can calculate this angle by using a property, a trigonometric ratio that we study in mathematics, and that angle would be uh, theta equals to tan inverse perpendicular over base. You don't want to do that, that's totally fine. Simply take out the protractor, put the reference line of the protractor over here and measure the angle, this one. I mean, apparently it looks somewhere 30 to 35 or maybe one, yeah, 30 to 35. Might be between 35 and 40 as well. If the question was find the angle between east and the resultant, then east is on this side, the resultant is in this direction, and the angle between east and the resultant would be this one. So the simplest way is if you don't want to use any of the mathematics, because at this stage, when the students are in O1, they may not be quite as good with the trigonometric ratios because they might not have even studied that. So the easiest way is just find the angle using the protractor from the given axis or from the given direction. Alright, so related to this concept, I'm going to solve a sample question that is from one of the recent past papers, 2021, paper 2-1 from May June session. An aircraft flies at constant height, so I'm going to skip all the some of the information, the description. You can see it on the diagram as well. We have one vector that is 12 kilonewton. The vector you call it is a force vector. It is a force, and it is uh, yeah. One of the forces acting on the airplane is towards the east, that is 12 kilonewton. The other one is towards north, that is 36 kilonewton. And the question is, draw a scale drawing to show the resultant force acting on the aircraft. Use your drawing to determine the size of the resultant force. So we need to find the magnitude of the resultant force and the angle between the resultant force and north. So this is the same thing that I was saying, that if they want you to find the angle of the resultant force, they would mention where do you need to find the angle from. All right. If it's not mentioned, then there's a certain case that you always take the angle from positive x-axis, you move counterclockwise, but they don't test this thing in O levels. So in O levels, they do provide the information that which angle do you need to come up with, or which angle needs to calculate it, and from where it needs to be calculated. So first of all, let us choose a proper scale. This is the most important thing. You have to be logical here. There's not there's no formula that you can memorize so that your scale would always be uh, normal or just a standard one. So sometimes the scale might be different for two different students, and both of them might be correct. Both of their answers, the answer for both of the students might be accurate, even with the different scale. So in this case, what I'm going to do is I say 6 kilonewtons every 6 kilonewtons would be represented by 1 centimeter. Alright, so I'm choosing a scale that would fit on the sheet of paper, not on my like drawings here. That would be suitable for the sheet of paper, and for the space, like that much space, the scale that should be suitable for that much of the space. So if so, this is my scale. I mean, every 6 kilonewton would be represented by 1 centimeter. So I can give the heading scale over here, and then if 6 kilonewtons represents, every 6 kilonewtons represents 1 centimeter or is represented by 1 centimeter, then 12 kilonewton would be represented by 2 centimeters, and 36 kilonewtons would be represented by 6 centimeters. How do we do that? I mean, if you're not good with it, you can simply cross multiply once again. Now what we do is I draw a line that is 2 centimeter towards south, sorry, towards east, and that is 6 centimeter towards north. So first I'm going to come up with the line that is uh, 2 centimeters. Let's say this is 2 centimeters towards east, which is representing this one, 12 kilonewton. This is 2 centimeters. And then I have to draw a line that is 6 centimeters, and that line should be towards north. Alright, and if you want to skip a step and you want to like uh, don't want to waste so much time in it, just draw the second vector directly at the end of the first one, and the second one should be 3 times as big as the first one, because it has to be 6 centimeter. But for you guys, you're doing with the scale, so you don't have any problem with it. Use the ruler, draw a line that is 6 centimeters in length, exactly in 6 centimeters in length. So this one, let's say this one is representing 6 centimeters. Now, in order to draw the resultant vector, I have to draw a line that is starting from the tail, that is starting from the starting point, and that is pointing towards the end point of the diagram. So I'm going to draw a green line that will be representing the resultant force, the resultant vector, let's say for now. And the direction of this one is over here. Alright, away from the starting point and towards the end point. This is the direction of the resultant vector. Now, size of the resultant force. I need to find the value of the resultant force. So the first thing is you measure the length of the green line. The green line is representing your resultant force. So you measure the length of the green line. How do you do that? Just place the ruler along this green line and measure like how many centimeters it is. So I'm not using the calculator, I'm using the ruler, and the length of the line according to the ruler is 40 and square root of 40. 6.3. And yeah, I didn't use the ruler. Uh, I didn't use the calculator, I used a ruler, and the length of the line was 6.2 centimeters. Once again, if you want to get away, once I have written the value of the line is 6.2 centimeters, you can check here on the calculator, you can measure the length of the line from the ruler as well. Both values ideally should be equal, but can be a little bit difference. That is acceptable. A minute difference of let's say 0.01 millimeters, 0.05 millimeters. that would be acceptable. So the next thing is, once you have measured the length of the line, this line is 6.2 centimeters. How many kilonewtons this line would represent? According to the scale, every centimeter represents 6 kilonewtons. 2 centimeter would represent 2 times 6 kilonewtons. 3 centimeters would represent 3 times 6 kilonewtons. So 6.2 centimeters would represent 6.2 times 6 kilonewton. So this one, once again, you can hit it on the calculator. 6 times 6.2. 6 times 6.2. Sorry, they're wrong. 6 times 6.2. 37.2. So what I get is 37.2 kilonewton. If you want to write the answer in two significant figures, that can be 37 and yeah, 37.2 kilonewton. That is the size of the resultant force. When they say the word size of the resultant force, that means magnitude, the numeric value along with the unit. Alright, so the next step was we have to find the angle between the resultant force and north. Angle between the resultant force and north. So north is like straight up. According to the mapping system, this is the north, and you need to find the angle between the north and the force. So once again, the easiest way is simply find the angle using the compass, using the protractor. So what I'm going to do is, so I can draw the normal line here. Once again, so let's say this one is representing the north. Sorry, north. You can draw the north once again. And you can find this angle, which is the angle between the north and the resultant vector using the protractor. And yeah, I just saw it again once again on the calculator. This line, when you measure its length, it is 6.32. I mistakenly wrote 6.2 here, and the answer that you get for the resultant force would be 37.9, and in 2SF you can write it as 38. So 6.32 is the length that you get not only from the calculator, but you'll be getting the same from the uh, ruler as well, provided there's no other mistake. Then you need to find the angle between north. North is a vertical line directed upward on the sheet of paper. You measure the angle, and this one was your resultant. You measure the angle between these two with the help of a ruler, and you get your uh, answer for the angle. If you don't want to use it, measure it with the help of a protractor. Sorry, not with the help of a ruler. I said mistakenly with the help of a protractor. So if you don't want to measure with the help of a protractor, you want to use some laws of mathematics, then you know this angle according to this diagram equals to this one angle as well. So let me take a different one over here. Yeah. So if somehow you're able to find this one angle mathematically, that would be the same angle between north and the resultant vector. So once again, I mean, if you had drawn the north over here, that would have been the same thing. But easiest method I've explained already. Just seeing from the description, you need to find angle between north. Align your protractor with the north, right? Align your protractor with the north like this, and find the value of this angle. Right? It should be pretty simple, but Mathematically, you can find this theta, but using the formula, that is theta equals tan inverse perpendicular, which is opposite to the theta. Perpendicular is 2 divided by base, that is making 90-degree angle with the opposite, which is 6. Then you hit it on the calculator, tan inverse 2 over 6. 2 over 6 is 0.333. 3 continue recurring. You take tan inverse of it. Alright, shift on calculator, you press the shift button, then you press tan button, you get tan inverse. Then you press 0.33 or you insert the same value, tan inverse of answer, and it would be 1/8. 18 degrees. And we understand once you'll be advanced enough in mathematics as well, you'll find out that the angle between that is measured from the north, we call it bearing, and that is written in 3 digits, 018 degrees. Alright, because the maximum angle that you can have is 360, so just for the convention, we try to keep it 3-digit number, so 18 would be written as 018. That's just a convention, a tradition. Even if you write 18 degrees, that would be fine. I mean, so 18 degrees to get from here, that is the same angle between north and the resultant vector. So this is how you can find the magnitude of a vector and the angle of the vector by using scale drawings. The same question can be done by using the Pythagoras theorem only without drawing anything, but in this one they had mentioned explicitly draw a scale drawing. So you have to choose a scale for it. You have to, according to the scale, you have to draw the lines using the ruler on the sheet of paper. Then you do the calculations like this, like measuring the length of the resultant vector using the ruler, multiply that length back with the help of the scale to find the actual value of the quantity that you need to measure. So that's it for this video. I'll be back with another one. Subscribe to the channel as well, and you can hit the like button as well. Thank you everyone.